Okay. Hey, chemistry friends, we are back again. Sorry, let's get where we started. Yesterday, we just did basics on gas laws and properties of gases, and today we're going to bring in more. We're not going to quite hit the math yet. We'll do that tomorrow. But we have two gas laws that we are going to study in this unit. One is called the combined gas law, which we're going to talk about today, which is what it is. You'll see in a moment. It is a bunch of different gas laws combined. And then the ideal gas law we'll do in a couple of days after we get some math going. Anyhow, and hopefully on day 2 you won't have as many Schoology issues, but we'll work through it. It's okay. The homework and stuff right now is just for practice till we make sure everybody is up to speed on using their technology. Anyhow, we had looked at pressure, volume, temperature, and amount as all the factors that can affect a gas and how it behaves. Okay. Some are easy to kind of figure out, some are a little more subtle, but now that we have those factors behind us, we are going to talk about the combined gas law and what factors go into it and get the formula set up. First, we got to talk about our friend Avogadro. That brought us the mole, and we should know by now from back in moles that, you know, we have Avogadro's number. When you were doing the particle to mole thing, it was 6.02 times 10 to the 23rd. Where did that come from? Well, Avogadro's big work was in gas, and the mole really came from studying the relationships of gas because they are nice, linear, wonderful relationships. Okay, so that was the work that really led him to the mole, although it was many years later, 50-ish, I can't remember, years later that somebody actually came up with that 6.02 number. Anyhow, the point is it brought us the mole and really ushered in the age of chemistry being a physical science that you can predict. Okay, so what was known at the time from experimentation was that if any gas, okay, all gases, when heated, equally expanded by the same exact amount volume-wise. Avogadro took that farther with his experiment and said that two equal volumes of gas, if they were at same temperature and pressure, contain the same number of particles. Okay, and that could mean atoms or molecules or whatever. But if you had two of the same volume and you heated them and you had them at the same temperature and pressure, they're going to have the same number. Okay, and if you like the Italian type words, I gave it to you there. Anyhow, let's talk a little bit about temperature and pressure. We talked about pressure in our last video. Okay, and you'll hear this term standard temperature and pressure often, and really that's kind of the initial Avogadro, same temperature, pressure kind of stuff that we're looking at. Okay, standard temperature, which was where the testing started, and then you could change pressure from there, is 1 atmosphere. It's also the same value in kilopascals as 101.3, the same value in millimeters of mercury, 760. It doesn't really matter. They're all the same. They're just different units. We will really be sticking to atmospheres in kilopascals, but that, if you ever hear standard pressure, that's a number you want to use. Standard temperature is always 0 degrees Celsius, but we don't work in Celsius. And let me talk about temperature. You have Celsius, you have Fahrenheit, you have Kelvin. Okay, Fahrenheit is garbage. Okay, although God bless America, we still use it in the USA. Fahrenheit is garbage because it's literally, there's no equal distance from 1 degree to the other. It was almost set up to be, it's almost like some guy stood out there and said, 32 is freezing. That's what it feels like. And, whatever. Celsius is better because it is an exact increment, same increment every degree all the way up or down. Kelvin is the best, and this is why Kelvin, any math we do in this unit has to be done in Kelvin, is because Kelvin never goes below 0. Okay, it's a simple conversion. You take your Celsius temperature and add 273. Okay, so at 0 degrees Celsius, you're at 273 Kelvin. Okay. And no matter what goes below, now there is a value called absolute zero, and we'll demonstrate that a little bit with a lab, either when we get back together or I'll film it. Absolute zero is when Kelvin is at zero, and that'd be minus 273 degrees. That is a theoretical number. It has never been, although they've come close, it's never been approached in the lab. And part of that question is, if you get there and molecular motion stops, what's going to happen? It's very hard to get there because at that point, even with the gas and stuff that you're using, they're still going to solidify and stuff at that point. Anyhow, that's the theory. Okay, so temperature always in Kelvin. Standard temperature is always 273 Kelvin. Standard pressure is 1 atmosphere. Okay, so let's talk about the combined gas law. It's called the combined gas law because that's what it is. It's a combination of 3 other experimentally determined gas laws we're going to look at separately here. Okay, and of the 4 factors that affect a gas and its behavior of expanding, contracting, temperature, pressure, changing, whatever, it's the one you can use when it's where the amount of moles are always assumed constant, that they're going to be held constant, and you figure out how the other factors are being affected. Now, you have 4 factors that affect a gas, and really the only one you can actually hold constant is the amount, the number of moles. Okay. You cannot do a viable experiment with then 3 other variables trying to keep them measured and keep good quantifiable data, which is why then you have to, why we had the other 3 laws. You have to then kind of look at them in pairs of 2, like pressure and volume, okay? And assume you're not only holding the amount constant, but also the temperature, or pressure and temperature, assuming you're holding the volume constant. That's really the only way you can do things effectively. And that's how it was done over a series of a number of years, and then they were all smashed together into the combined gas law. Okay. One thing to tell you before we start and do math is that gases are linear. Okay. So when you compare those 2 variables, whether it's pressure, temperature, volume, temperature, whatever, you are going to get a straight line. And that slope of the line is constant, so that's going to give you your value of going from a proportional relationship to an equality. And so you can see at the bottom, this is the combined gas law, but let's figure out how we got there first. Okay. And again, this is what I'm saying. You can't do 3 variables at once, so these are the variables that they look at and pair them up, and that's what we're going to put together. Okay. So the first one we're starting with is Boyle's law. It was named for Charles Boyle, studied the relationship between pressure and volume. And what he determined was, for the same amount of gas is being held constant and temperature is being constant, you get an inverse or indirect relationship. So when one goes up, the other goes down. So if pressure goes up, volume goes down, and vice versa. Okay. Again, assuming that you're keeping temperature and moles constant. It is our only indirect relationship in the group. Okay. So again, pressure increases, volume is going to decrease. If volume increases, pressure is going to decrease, that kind of thing. Okay. And here's your graphs. And I'll show you a little animation in a minute. That's where suppose you have a cylinder with a piston on the top that you can change the volume. And you have a gauge to measure pressure, okay? And it's in a container, so the amount is constant, and it can be maintained at a constant temperature. What you see then is your indirect relationship. As pressure increases, volume decreases, okay? Now, if you remember your algebra and your inverse relationships, the way to get then your straight line is to flip over one of those values. So get the reciprocal of, say, here, the volume, and you can see it straightens right out to show that indirect relationship. Okay. All right. And here's the animation I was telling you. So here you go. you've got this container, you're holding it at a constant temperature, you have an exact amount of gas in there. You can see your indirect relationship occurring, okay? Temperature is being held constant. As the pressure increases by these weights, then the volume decreases. Okay? That's the idea. Okay? How do we turn that into algebra and get the formula? Well, okay, as you saw by the math and the graph, the pressure is inversely proportional to the volume. And think algebra, if you have a proportionality, you can make an equality when you multiply by a constant. Okay? So take the inverse of the volume, multiply by a constant, that'll give you the pressure. Okay? And rearrange that algebra. Well, then that means that P times V is that constant. Well, what's that constant? That's the slope of the line. Every one of these P's is going to have a V, or an inverse of V, that is going to be attached to it. Okay? And it's always going to be the same constant. So if a point down here has the same slope as a point up here, then they are equal to each other. Okay? So that's where Boyle's law, you can see, is the top half of the combined gas law. P1 times V1 is P2 times V2. Okay? And so you would get 3 out of 4 of those values, say 2 pressures in one of the volumes and find the other volume. It's just plugging in the math and solving. It's real easy plug and chug stuff. Okay? The one thing you always want to be careful of is make sure your values match. You know, that your volumes are the same units, your pressures are the same units. Okay? Let's show you an example. Say you have a balloon that has 30 liters of helium at 103 kilopascals. So you have here's your V1 is 30 liters, your P1 is 103 kilopascals. What's the new volume? What's the volume going to change to as that helium takes it up and you get to an altitude where the pressure is only 25 kilopascals? So your 30 goes in V1, your 103 goes in P1, your 25 goes in P2, and you're solving for V2. And if you plug it all into that formula and do things, then you should find out that it's going to expand to 124 liters. I don't know what the balloon's made of, but that might bloat it up depending on how big a volume it's allowed to carry. Don't know. Okay? So that's Boyle's law. That takes care of the pressure-volume relationship. And again, everything we're looking at today is assuming the amount, because it's a combined gas law, that the amount of gas is never changing. So it's a good gas law to use when you just have really a single gas making a change. Okay? You know, something like, and where would I use things like this? Flying airplanes, scuba diving, driving a submarine. Okay. The next law is Chucky, and Chucky's volume temperature. Okay. Jacques Charles studied volume and temperature. This was after Boyle. Boyle was the first. Okay. And this is a direct relationship, and that might make sense. And that might be more obvious. As the volume increases, the temperature increases. If the temperature decreases. So as the temperature goes up, things are going to speed up. You're going to expand that volume of that gas. As the temperature goes down, things are going to slow down. That volume is going to contract. That's the idea. Simple direct relationship. You can see the graph right here. Don't worry about the dashed lines. That's just the estimated, extrapolated data from what they had here. Again, this is something we'll look at because you extrapolate the graph back and you can figure out roughly where absolute zero is. Okay. Again, I'm going to show you a graphic with that same cylinder with the piston. So you can change the volume and you have that heating, cooling element to change the temperature. We're going to keep a constant force of weights on the piston to keep the pressure constant. And again, it's always amount. In all these, the amount is always constant. And in this case, for Charles' law, we're holding the pressure constant. Okay. And what we should see is an increase in temperature, increases volume, a decrease in temperature, decreases volume. Now, we're not going heavy into the math today, but I have to keep reminding you, this is the #1 error we see on quizzes. Temperature always has to be in Kelvin because you can't have a negative volume. You can't have a negative pressure. So you have to use the temperature scale that never goes below 0. So you always have to use Kelvin, which again is just adding 273 to the Celsius temperature. Okay? And there's our graph. And you can see we're keeping our 2 little weights here for a constant pressure. We heat it up, we cool it down. We have the same number of particles going on. As it heats up, the volume expands. As it cools down, it goes down. A nice direct relationship. Okay? All right. Formula time again. Same thing. So volume then is directly proportional to the temperature. Okay? Make an inequality. You multiply by that constant. What's that constant? The slope of the line right there. Then I can rearrange it, okay, and get the constant by itself so that if I have 2 constants equal, then the 2 parts are equal. Okay, and it becomes V over T is K. All right, so think of the combined gas law. Now we're holding pressure constant, so it's not really a factor. It's canceling on both sides. Then V over T equals V over T. So Chucky's law is V1 T1 equals V2 T2. Okay. Now, here's our example again. We have a gas at a volume of 25 liters and a temperature of 303 Kelvin, always working in Kelvin. Okay. Will expand to what volume if you crank up the temperature to 400 Kelvin? Okay. So again, you have your initial volume V1 at 25. You have your initial temperature T1 at 303. You have your next temperature is 400 Kelvin, so you're solving for V2. So it's plug and chug math. One thing students love this unit for nothing other than the fact that it's very simple plug and chug formula algebra. Your biggest errors are going to be 2 things. Make sure temperature is always in Kelvin, and make sure when you have V1 and V2, they are the same units. Okay, they have to be the same thing. It doesn't matter what they are, but they both have to be liters or milliliters or gallons or whatever it would be. Okay. Anyhow, we plug it all in, we do the math, and if I did my math correctly, then it should expand to about 33 liters. Okay. All right. We have one more, and then we'll smash them all together into the combined gas law. And the last one is Guy Lussac, another French guy. Okay, and this was pressure and temperature. So now we got the volume constant, the amount has always stayed constant, and what you see again is you have another direct relationship. As the temperature goes up, the pressure goes up. As the temperature goes down, the pressure goes down. That makes sense. As you speed things up, as we talked about pressure yesterday, and you're in a set volume, then those particles are going to be hitting the side of the container more often, increasing the pressure. If you slow them down, if you cool it down, then they're not moving as fast. Then they're not hitting the side as often. Pressure's going down. Okay? All right. So you have 2 direct relationships, pressure, temperature, volume, temperature. You have 1 indirect, volume and pressure. Okay? And there you go. You see the graph right down on the lower right-hand corner. There we go. Okay. And again, we're going to have the same cylinder. We're going to fix the piston so that the volume is constant. We know the amount is going to be constant. We have the heating, cooling element to change the temperature. And you'll see in this one, they demonstrate the change in pressure by just adding in little green weights. Okay. And it's the best cartoony way to illustrate it. Again, when you do these problems, temperature has to be in Kelvin. Please make sure it is. There we go. Here's our direct relationship graph. You can see as you, oh, the flame didn't show up, but as you increase the temperature, sorry, our flame is missing. We're holding the volume constant, we're holding the amount of gas constant. As the flame goes up, the weights go up, and as the temperature goes down, the pressure goes down. Okay. Let's get our formula going again. Again, it's just like Chucky's law, except we're looking at pressure and temperature. They are directly proportional. As one goes up, the other goes up. As one goes down, the other goes down. You can always make that an equality by multiplying by the constant. What's the constant? The slope of the line on the graph. Rearrange the formula, and now you see P over T equals K. Okay. Since all of those points have the same K value, I can compare any two of them. So say this was P1 and T1, and this was P2 and T2. If I had three of those four values, then I can just plug them in and find out the fourth value. Okay. And again, if you think of the combined gas law overall, all we did was break it into parts. PV on the top equals PV on the top, V over T and V over T, P over T, and P over T, on both sides, and there we go. Okay. So here's again an example. You have a gas at a pressure of 1.5 atmospheres and a temperature 273 Kelvin. Bad language will increase to what pressure? A gas at pressure of 1.5 and a temperature will increase to what pressure if the temperature is increased to 450? Now, just by looking at the graph, and this is a nice thing about gas laws, see if it makes sense. Because we know if the temperature is going up, the pressure should go up. So if you do your math and it doesn't follow what the law says it should do, then you had an error in your math. Okay, so take that pause to think about your answer. Anyhow, so our P1 is 1.5. Our T1 is 273 Kelvin. Our T2 is 450 Kelvin. We're solving for P2. Plug it in, solve away, and if we do it correctly, then it should increase to 2.5 atmospheres. Now, you might go, well, 1 atmosphere, that in the whole, that's a lot. That's a lot. Atmospheres is a nice pressure unit to use because it has very small manageable numbers, but that difference in 1 atmosphere is huge. I mean, that's 101 kilopascals. Same difference. So it is big. Okay. All right. So that's the three parts that go into the combined gas law. Then we smash them together. Okay. Combined gas law is then just putting together Boyle's, Chucky, and Gay-Lussac. Okay. And the reality is this: the only thing you can really hold constant is the amount. Okay. Because the other three are going to, pressure, volume, and temperature, are always going to interact and affect each other. We're talking gases here. The only way to hold a gas constant volume-wise, of course, you put it in a container, but that's only the container staying constant. The gas is expanding and contracting within that container. Okay. Which is, again, then changing the pressure. You really can't hold that pressure constant even though it's in the container. I mean, in little small amounts you can, but you really can't quite hold it super constant because it's going to be affected. As the gas expands or contracts, that also talks to how the temperature is going to go. So it's not a big enough factor to not allow the math to work, but that's the only way to figure out the combined gas law was to take those variables separately and realize that really pressure, volume, and temperature are always affecting each other to some extent. Okay. But not enough to goof it up. Anyhow, so here's the formula, and think about it. Just if you were to just eliminate the T's out of here, then you would have P1 V1 as P2 V2. Okay. If you were to eliminate the P's, say pressure was constant, then you got V1 over T1 as V2 T2. That's Chucky's law. If, say, for some reason you were assuming the volume was constant, now you got P1 over T1 as P2 over T2. So because of the linear math and because of the relationships, you can smash them all together although you can't really draw a great graph of it. But that then means that pressure, volume, and temperature at a constant amount are all going to meet for a particular gas at the slope of the line, just like we saw in the others. And so if the slope for one set of points is here on the same slope as, and has the same slope as the other set of points for that gas, then their pressure volumes, then you can compare them. And that's where the P1 V1 over T1 equals P2 V2 T2. Okay? That's it. Unfortunately, you have to go through the other three to understand where that came from. Let's do a quick example, and then we'll be done for the day. I'll have a homework, little quiz again, a non-scoring kind of quiz, a few questions just to gauge your understanding with this also. So after we finish this film, please give that a shot and see how it works for you. Anyhow, here's our example. You have a gas that occupies 10 liters at a temperature of 273 Kelvin, and it's at a pressure of 1.35 atmospheres. Now, the pressure increases to 3 atmospheres, and the temperature changes to 325 Kelvin. What's the new volume? And again, be careful here. Keep values together. That could be another error. So your V1 is 10. Your P1 is 1.35 atmospheres. Your T1 is 273 Kelvin. That should be all on one side. Reading sometimes is very careful. Your P2 is 3. Your T2 is 325. Okay. And you're going to find the volume. All right. And make sure all our units match, which I wrote the problem so it would. You're going to end up in liters. Okay. Then solve for the volume. So here's what it's going to look like. You've got your atmospheres, your liters. Okay, so here's all your P1, V1, T1 values. Here's your P2 and T2 values. You're solving for what's the volume going to do. Okay. Now you can kind of think about it. The pressure's going up, so the volume should decrease. Okay. And the temperature is going down, up, so the volume should increase a little. This is sometimes with a combined gas law, you can't just eyeball it like you can do on the others, just because you've got a little competing action going on here. Pressure's going up, which should push the volume down, but temperature's going up, which should push the volume up. It's going to land linearly somewhere a little betwixt in between. It just depends on which one has more power at that point, which one's the bigger change. Anyhow, as far as the math, now it's plug and chug. Atmospheres cancel out. Kelvins cancel out in our dimensional analysis. You see the only thing left in liters. And if I did my math right, then it should go down to 5.3 liters. So it did drop some because the pressure had a little more power and a little more influence than the temperature did. Okay. All right. That's the idea. Anyhow. We'll do for tomorrow, tomorrow's lesson will just be a few straight examples, and then I'll actually put up a homework sheet for you to do on your own, not a little quiz, but a homework sheet with a few problems on it for you to do. And then you can download, you'll be able to download it in Notability and stuff, but that's tomorrow. Today, we're going to just finish this. And as we have now, there'll be a little few question quiz homework kind of thing on Schoology that I'd like you to complete. Okay. All right. Thanks for your attention. I hope on day 2 and stuff here, you're getting into routine and enjoying stuff. I honestly miss being in the classroom with you and just doing this virtual, but hopefully after May 4th, we are back together. Anyhow, have a good day. Stay healthy, stay positive. And enjoy the rest of your day.